We've seen that orthonormal bases are the best kind of basis for several reasons. So it would be really nice if we had some way to come up with orthonormal bases. They are very nice, but they're also kind of rare because there are so many conditions that you have to get just right to have an orthonormal basis, right? So many dot products have to be just so. So it would be nice if we had some way to start with a regular basis, any old basis, and turn it into an orthonormal basis. Just in R2, if we had a basis like this, and suppose these vectors aren't unit length like this, right? This is a basis because these two are linearly independent, but first of all, they're too long, and second of all, the angle between them isn't 90 degrees. So what could we do to make them orthonormal? So let's concentrate on getting the angles right. If we can get all of these vectors in our basis to be perpendicular, getting them all to be unit length is pretty easy. You just scale them so that they have unit length, right? If we have any vector u, we can make it unit length by dividing it by its own magnitude. So if we can get perpendicular vectors, making them all unit length is going to be pretty straightforward. So let's concentrate on making them perpendicular. Well, for these two vectors, right, how could we, right, we don't want to change the span of these two vectors. We want to, at every stage in this calculation, we still want to span the original space so that we end up with a basis for the original vector space. So we don't want to change the span of these two, which means the best we can do is add a multiple of one vector to another, right? Because that won't change the span. So what we can do is, we can add any multiple of, let's call this one u1 and this one u2. We can add a multiple of u1 to u2, and that means, right, adding a multiple of u1 to u2 is going to let us slide the end of u2 in the direction of u1. So we could replace u2 with a vector starting at the origin, and that ends anywhere on this dotted line. But you can see that right here is a spot that if we slide the end of u2 along this green arrow, the result is perpendicular to u1. So that's what we want to do, right? We want to replace u2 with this new vector. The span will be the same. The span of u1 and this new vector will be the same as the original two, but these two vectors are perpendicular. Well, this is exactly the orthogonal complement that the dot product gives you, right? So this is just the original vector, but then you subtract the projection of u2 onto u1. Right? The projection of u2 onto u1 is this yellow vector here. And you can see the green vector is just the negative of the yellow one. So what we can do is u1, our first vector, let's just leave it alone. So what we're going to do is we're going to start with these u's as inputs, and we're going to create a new basis called v's, so v1 through vk. So v1 is just going to be u1. So the first vector we can leave alone. Now the second vector, right, we're going to start with u2 so that we have the same span, but just like we did here, we're going to subtract off the projection of u2 onto u1, right? And that's going to guarantee that these two vectors are perpendicular. Okay, so now what do we do next? Well, we have v1. This picture is going to be hard to draw because it's three-dimensional, but we have v1 and v2, and they're perpendicular, right? They span some plane. And then we have this third vector, which is u3, which might be pointing out like this. And it's probably not perpendicular to v1 or v2. So how can we make it perpendicular to v1? Well, to get it perpendicular to v1, we're going to have to subtract off the projection of this is u3, sorry. Subtract off the projection of u3 onto v1. Right? There's some component of u3 that points in the direction of v1. So to get v3, we'll start with u3, but then subtract the projection of u3 onto v1. But, u3 probably isn't perpendicular to v2 either, so we're going to have to subtract off the projection of u3 onto v2. Now this is actually, subtracting off this second projection actually might mess up our previous step, right? Because it's possible that if you have, so this first difference, u3 minus this first projection, this is perpendicular to v1, right? Because this is just the orthogonal complement relative to v1. It's possible that subtracting this other vector will make the entire thing no longer perpendicular to v1, so that's a possibility. But in this case, this doesn't actually happen. We will check this in a moment, but this doesn't actually happen because v1 and v2 are perpendicular already, right? So it turns out that that's the key thing. Since we already have these two perpendicular, this second subtraction doesn't mess up the previous orthogonal complement. Okay, so now, so we know already that v1 is perpendicular to v2. Now let's check that v1 is perpendicular to v3. So how can we check this? Just take the dot product, right? Take the dot product of v3 and v1. So v1 dot v3 is u3 dot v1 minus the projection of u3 onto v1. So v1 dot, so this projection is u3 dot v1 over v1 dot v1 times v1, right? Okay, so that's v1 dotted with this first projection, and then also we have to distribute this v1 to this third term. So v1 dotted with this projection is u3 dot v2 over v2 dot v2 all times v2. Okay. This last term, right, we already know that v1 is perpendicular to v2, so this last term is 0, right? Because we have v1 dotted with a scalar multiple of v2. So this last term is 0. Okay, so we're getting u3 dot v1 minus, now we need to work out this mess. We can pull this scalar multiple out in front. So u3 dot v1 over v1 dot v1. And then it's this vector dotted with that vector. So v1 dotted with v1. But look, here's v1 dot v1 in the denominator, so these cancel. So we're getting u3 dot v1, but this one's negative, that one's positive. These cancel, and you get 0. So now we know that v1 dotted with v3 is 0. We should also check that v2 dotted with v3 is 0. But it's the same kind of calculation, so I won't drag you through it. So that means that these three vectors are all perpendicular to each other. Okay, so now we need to continue on to the fourth. So again, we'll do just like what we did for u3. Starting with u4, we'll subtract off the projection of u4 onto our previous vectors, our previous v's. So subtract off the projection onto v1, subtract off the projection onto v2, and subtract off the projection onto v3. Okay, and now we would need to prove that v4 is perpendicular to v3, v2, and v1, but that calculation will go exactly the same as these previous ones did, so let's not write it out. Well, at each step you can see what we're doing is we're just starting with the u for that step and then subtracting off the projection onto previous v's of that u. So I guess we need a sum from j equals 1 to I minus 1, right? Okay. So for each step, you just take that u vector and then subtract the projection of that u onto the previous v's. So what this gives us is a collection of vectors vk that have the same span as the u's that we started with, and all of these things are perpendicular to each other when I isn't equal to j, right? A vector can't be perpendicular to itself except the 0 vector. So these things are pairwise perpendicular. So this is an orthogonal basis. It's not yet orthonormal because we don't have unit vectors, but it's easy to make these all unit vectors. So now for each vector, for each vector in our basis, just divide it by its own length, and that'll make it a unit vector. So w1 is now v1 over magnitude of v1. Down to wk is vk over the magnitude of vk. Now the w's have the same span as the v's, and so also the same span as the u's. We have that wi is perpendicular to wk when I is not equal to j. Sorry, I need a j here. This is because, right, the v's had this property, and to get the w's, we're changing the lengths of things, but we aren't changing the angles between any of these vectors. So they were all pairwise orthogonal before, so they're pairwise orthogonal after. And then finally, the length of each one of these vectors is 1. But these together mean that the w's are what we're looking for. They are an orthonormal, I'll abbreviate that, orthonormal basis for the space that we started with, which I think I called V. Okay? So this process of producing an orthonormal basis, it's called the Gram-Schmidt process, and it's sort of a two-step thing. First, you come up with an orthogonal basis. Right? For your first vector, you just leave it alone. For the second one, you take your second starting vector, subtract off the projection onto the first, and then for the third, you start with the third vector, subtract off the projection onto the first two, and so on. When you're done, you just scale them all so that they're unit length, and then you have an orthonormal basis. So it's always possible to come up with an orthonormal basis for any subspace in Rn. And in fact, if you come up with a basis for a subspace, you can then use the Gram-Schmidt process to make it orthonormal. Then you can extend that basis to all of Rn and then make that orthonormal. So what you end up with is an orthonormal basis where some of the basis vectors serve as an orthonormal basis for your subspace, and the other vectors in the basis extend that in an orthonormal way to the rest of Rn. So it's, everything we could do with regular bases, we can do with orthonormal bases as far as, producing nice bases adapted to subspaces. Let's look at an example of actually using this Gram-Schmidt process, because the calculation is kind of annoying in that it's large, but it's not hard, right? So here's, I called these u's before. Let me call these u's. Okay, so we have this basis for this subspace V, right? Subspace is just the span of these two vectors. So let's find an orthonormal basis for V, because this basis is clearly not orthonormal, right? The length of these vectors is not 1, and also the dot product of these two is not 0. So remember, the first thing that we do is we come up with an orthogonal basis, and the first vector in our orthogonal basis is just the same as the first vector in our original basis, so that's 1, 2, 0. Okay. Now to get the second vector in our orthogonal basis, we start with u2, but then we subtract off the projection onto v1 of u2. And that's v1 dot u2 over v1 dot v1 times v1. Okay, so u2 is 0, 1, 2 minus, and then for this fraction, the numerator is the dot product of v1 and u2, so v1 and u2, and the dot product of those is 2. And then this denominator is v1 dot v1, and it looks like that's 5. Okay, times v1, which is 1, 2, 0. Okay, so we're going to get, let's see, minus 2/5, and then 1 minus 4/5, so plus 1/5, and then 2 minus 0, so just 2. Okay, now if we've done our jobs right, v1 dot v2 should be 0 at this point, right? These two vectors should be an orthogonal basis for this space, and if you take the dot product of this and that, you do indeed get 0, so that works out. So now we have an orthogonal basis for v. Now we need an orthonormal basis, so that's going to be our w's. So just take each one of these vectors and divide it by its own length. So let's see, the magnitude of v1 looks like it's the square root of 5, and v1 is 1, 2, 0. So we could leave it like this, but I don't know, for some reason I feel like I ought to move this inside, so 1 over root 5, 2 over root 5, and 0. So there's the first vector for our orthonormal basis. The second vector for our orthonormal basis is going to be v2 over magnitude of v2. And this is going to be gross, unfortunately. So let's see. v2 is, maybe it would be easier to write v2 as 1 over 5 times minus 2, 1, 10. So let's do it that way. So because what that lets us do is the magnitude of 1 over 5 times minus 2, 1, 10. It's just, magnitude. It's 1 over 5 times the magnitude of minus 2, 1, 10. Right? You can just pull the absolute value of the scalar outside of the magnitude calculation. So we're going to get 1 over 5 times the magnitude of minus 2, 1, 10. So that's, let's see, 100 plus 5, so 105, square root of 105. Okay, so there's 1 over the magnitude. Now we need to multiply by v2, and v2 is 1 over 5 times minus 2, 1, 10. So this 1 over 5 cancels this 1 over 5. So we get 1 over square root 105 times minus 2, 1, 10. Okay, and this one, why don't we, there was no need to put that square root in there. So 1 over square root 5 times 1, 2, 0. Okay, so this should be our orthonormal basis, right? Now, because of how we computed it, it's guaranteed to have the same span as these vectors that we started with. So it is a basis for v. The only question is it an orthonormal basis? Now it should be because we used the Gram-Schmidt process, but let's just make sure. So let's calculate w1.w1. This should come out to be 1. So w1 is 1 over root 5 times 1, 2, 0. And we're dotting this with itself, so 1 over root 5 times 1, 2, 0. So we can pull these two factors of 1 over root 5 out to the front, so they give us a factor of 1 over 5 times 1, 2, 0, dotted with 1, 2, 0. But 1, 2, 0 dotted with 1, 2, 0, that's 5. So this whole thing is just 1. Good, it was supposed to be 1. Now let's calculate W2 dotted with W2. So this is 1 over root 105 times minus 2, 110 dotted with 1 over root 105 times minus 2, 110. Okay, again, we can pull these square roots out to the front, and that gives us a 1 over 105 times the dot product of minus 2, 110 with itself. And of course, the dot product of minus 2, 110 with itself, that's 105. So again, we just get 1. Good, so both of these W's have unit length. Now let's check that they're perpendicular. So let's calculate W1 dot W2. So this is W1 is 1 over root 5 times 1, 2, 0. We're dotting that with W2, which is 1 over root 105 times minus 2, 110. Okay, let's pull the scalar factors out to the front. So 1 over root 5 times 1 over root 105 times the dot product of 1, 2, 0 with minus 2, 110. And the scalars in front don't matter because this dot product is clearly 0. So we get 0, right? So these two vectors are perpendicular as they were supposed to be, and their unit length. So these W's form an orthonormal basis for our subspace V.